Hello, everyone. I'm Joseph Bell, and this is my senior capstone presentation for my project, which was the design of an electrical conductivity sensor for measuring salinity. So I kind of want to discuss what is the importance of salinity and why measure it. So generally, you can use salinity in the measurement of it to study the marine environment, which would include, but is far from limited to, studying the hydrological cycle, where you have processes like evaporation and precipitation. You can have effects on marine life or marine ecology. You can study things like the intrusion of saltwater or freshwater. And something that I kind of discovered in a summer internship last summer with uh, Dr. Kamal was that you can use in situ measurements of salinity to validate ocean model data, numerical ocean model data. On this bottom left figure, you can see that this is model output for 2019, February 27th. This was 2 days before the first opening in 2019 of the Bonnie Carey spillway, which led to a massive intrusion of freshwater, which was being diverted from the Mississippi River to protect the levee systems. Here on the right, the figure is indicating model data again for salinity, and this is some 5 months after the initial opening of the Bonnie Carey spillway, where it is coupled with colored circles that are indicating in situ data measurements of salinity, stationary measurements that were performed by University of Southern Mississippi. And being 5 months after the spillway, where the spillway was opening for weeks at a time, you can see a massive intrusion of fresh water, which had a massive impact on the Gulf of Mexico and the economy and the marine ecology. And this is just the beginning of some of the importance of studying ocean salinity and why it's important to measure it. So I want to discuss kind of the concept of how salinity is measured. What is the process generally? So water salinity is measured by passing an electrical current, alternating current, or direct current between two electrodes, in this case, that are submersed in water, where water has the ability to conduct electricity. And this conductivity, or this conduction of electricity, or electrical conductivity of water, is influenced by the concentration of dissolved salts in the water. Where salts, when they're dissolved in the water, specifically these ions that disperse, they increase the ability of a solution to conduct electrical current. And a higher electrical conductivity value would indicate that it has a higher ability to conduct electrical current, which means that you have a higher salinity level, because salinity, again, is impacted, or it's measured, based on the amount of dissolved salts. So how is this important? How is electrical conductivity important in measuring salinity? That's because in the current that flows between the two electrodes in the water, there will exist a voltage drop. That is because while water has the ability to conduct electricity, it also is somewhat resistive or has resistivity. This resistivity will affect how much voltage drop occurs between the electrodes in the water. And by knowing the conductivity or inversely resistivity, one can calculate salinity. So I kind of want to discuss now, how do you measure these voltage drops and how can you begin to actually create a sensor which will measure this? And I kind of want to discuss something leading into that, and it is a method of measuring electrical conductivity, which is a four-probe measurement, where you have a current applied on the outer probes with an ideal current source. And I will discuss more about the ideal current source. But you have two outer electrodes, which are passing current, which follows these more horizontal lines between the two outer electrodes. And then on the inner probes, you have a measure of voltage, and these voltage measuring or sensing probes draw virtually zero current. The probes are probing at two different equipotential lines, where equipotential lines are lines of equal potential or equal voltage. So it is critical that these probes are spaced so that you can measure two different equipotential lines and thus find a difference in their voltages. These lines are also affected by the probe geometry, which is including the spacing of the probes, the material of the probes, as well as the actual physical size of the probes. And now I kind of want to discuss some of the, what are the advantages of using four probes? Why this rather than two probes? In a four probe concept or a measurement, you find that contact resistances due to fouling or things that may occur at the surfaces of the probe, what have you, they're very, very low with these voltage measuring probes. That's very important because you want to have accurate and precise measurements of voltage with these probes. And these probes not carrying any current, there's no issue with that. Also, you can measure very, very low resistance values. So revisiting with a 4-probe measurement, you have an ideal current source, where an ideal current source means that you have something that is outputting some signal where the current is independent of any resistances that you may have in the seawater. And this is critical because you, in accordance with Ohm's law, where you're measuring voltage, you know current, that allows you to calculate the resistance. So current does need to be constant, or in this case, you need to have an ideal current source. In my application, I am using a signal generator, where the signal generator is outputting an alternating current. And it's important to note that alternating current is not required for a 4-probe measurement. It is my application. The output of the signal generator in this case is 20 volts AC, where in series with this, where the current probe is leading out to, you have a roughly 5.1 kilo ohm resistor. Now, water, especially as the conductivity or the dissolved salts concentration gets higher, you'll notice that the resistance of seawater, which is indicated in the conductivity cell in the figure, the resistance of seawater is much, much smaller than that of the series resistor that has been added in this diagram. Therefore, from Ohm's law, if the series resistor is much higher than that of the resistance of the seawater, the total resistance can be assumed or approximated to be the series resistor. This allows you, when solving for current, to find that current is now independent of any resistance that one would find in seawater. It's important to note, too, that a benefit of using alternating current is that it mitigates problems with polarization, where polarization is the accumulation of charges at the current carrying electrodes, which negatively and wrongly affects your measurements. Now I want to discuss my implementation of the 4-probe measurements. On the left here is kind of a schematic or a kind of an example diagram of the electrical conductivity sensor that I created. It is of course, 4 probes, where the yellow portion is a 3D printed module that holds the 10 gauge copper probes. And the orange piece is also a 3D printed module that holds the bottom of them. This is simply just sits inside the cavity of the probe, and its purpose is to hold the probes in place. Now, the probe arrangement, they are collinearly arranged, which means that they're all on one line set up, and that the probes are also spaced uniformly, meaning that the distance between the current carrying probes to the voltage probes and again to the current carrying probes, they're all spaced the same amount. It's also important to note that the probes will extrude out into the water. That's very intuitive, but it's important to note that that distance, the extrusion distance, is going to affect things like the cell constant, where again, kind of going back to the previous slide, you see how this might affect things like current flux or equipotential lines. So again, this is just a reiteration of how a probe geometry is very significant in your electrical conductivity sensor setup. More importantly, one can calculate the cell constant by taking the probe spacing L and dividing that by the surface area of the probe, where the probe is nearly the surface area of a cylinder minus the 2 circular ends. So the probe spacing divided by the surface area of the probe, one probe, will give you the cell constant, which can be used to drive calculations for salinity. However, cell constants can more accurately and more reliably be determined by experimental methods, where you would use a conductivity standard or conductivity solution. On the right here, the right figure is my actual build of the electrical conductivity sensor, which is just an implementation of everything that you see in the figure on the left. So now that I actually have the sensor built, I wanted to, you want to perform measurements of voltage to find that voltage difference. So in this case, I use an oscilloscope where I'm connecting, as seen on the previous slide, the wires that come out of the top tether of the electrical conductivity sensor. I'm connecting to those wires with my oscilloscope probes. Channel 1 on the function generator is showing the output. Channel 1 on the oscilloscope is showing the output of the function generator, where it is 20 volts AC. I use this to trigger the signal where triggering is important because I have a repeating waveform where by triggering it, I can make it appear static. This is important for performing measurements. On channel 2, I have my first voltage measuring probe, as you can see in the top right figure. I have my first voltage measuring probe, which would have a higher potential than the second. So the pink indicates channel 2, the higher potential. The blue indicates channel 3, the lower potential. And by subtracting the higher potential, channel 2, and then the channel 3 or the lower potential, one can find the voltage difference or the load voltage. And it is the peak-to-peak voltage difference. That's important to note. Now, I did not perform this by hand. Modern oscilloscopes are equipped with a function called math that allows me to take the output, which is the difference of channel 2 and channel 3. Now, I want to discuss kind of why did I use two different channel inputs for the oscilloscope? Well, that's because I'm measuring with a reference to the ground, where the ground is the outermost probe, which is the ground of the current carrying source. I'm referencing to that because I'm unable to perform a floating voltage measurement like one would with a digital multimeter. Rather, I have to reference it to some ground, and thus I have to use two different channels. Now that I've used the oscilloscope to measure voltage, I kind of want to refine this and make it more accurate and reliable. And by doing so, I use what is known as a calibration curve. And I want to discuss what is that for and how does it apply to this situation. A calibration curve allows me to predict salinity, or PPT, the measure of salinity, for a measured voltage difference X. So how did I create this calibration curve? I created it using a commercial CTD, which is very, very accurate. And I used the readings of PPT from that CTD as a standard of PPT values. So using the RBR Concerto CTD, I was able to determine the PPT of many, many different solutions. By taking my electrical conductivity sensor, I was able to measure the voltage differences that exist for those PPT values. By comparing or having a relationship between known PPT or standard PPT and measured voltage difference, I'm able to create what is known I'm able to utilize what is known as a power regression model, where there exist many other types of regression models. I use a power regression model because it best fits the calculations that I find in my theory values. The form of a power regression model is y, where it is a function of x is equal to the coefficients a and b. I should say it's equal to a times x to the b, where a and b are coefficients that were determined in MATLAB using the power regression tools. So to kind of illustrate in the bottom on the orange, it is PPT as a function of voltage difference x is equal to 0.05103 times x to the negative 1.2271. This equation allows me to take my sensor and measure any voltage difference and apply that to this equation and thus predict PPT. So now I kind of want to show how does this apply and how do I implement this calibration curve, the use of the oscilloscope and the use of my probe. And this is what I'm discussing here is that in the figure on the bottom right, you can see where I have my signal generator outputting 20 volts AC, my oscilloscope reading in the voltages, my multimeter for reading current and making sure that it is in fact relatively constant or independent of the seawater, an ideal current source, I should say. In the purple, I have my electrical conductivity sensor submersed in some sample of water with an unknown resistance. And in the green circle, I'm indicating the connections of the oscilloscope probes and the signal generator probes to my electrical conductivity sensor wires. In performing this measurement, let's say I were to measure a voltage difference on the oscilloscope of 20 millivolts or 0.020 volts. Using 20 millivolts and evaluating it in the calibration curve equation, I'm able to predict that the PPT of this solution, this unknown solution, would be 6.2. So this is just kind of an application of how I've taken my electrical conductivity sensor in junction with an oscilloscope to measure voltage difference. And with that voltage difference, predict its corresponding PPT value. In summary, I wanted to kind of say, what I've learned. And really I learned the concepts of measuring electrical conductivity, and then from measuring electrical conductivity, how I could compute salinity and how to construct an electrical conductivity sensor's housing and electronics, really putting this together to be a physical product, something that I can use to perform measurements, stationary measurements. And some of the technical knowledge skills that I, knowledge and skills that I used and acquired would be the application of my knowledge in electronics from previous classes, learning how to use an oscilloscope and function generator, two things that I thought I knew how to use prior, but not quite well. I used soldering skills that I've learned in the past. I used numerical analysis skills in MATLAB. As well, I used Autodesk Fusion 360, a modeling software, to create the parts to hold the copper probes. And these are all really good things to be able to go back to and use again and kind of hone. And some of the soft skills that I used and acquired, every week we presented our information, our progress, our thought processes, and we had to articulate this into presentations and discussions. And that's more of a task than I'd realized, is communicating things clearly. I used public speaking and as well as listening to what my professors had to say and offer me so that I could do better in my project. Teamwork, working with my professors and my classmates, because you never know when you'll need to ask somebody a question. And lastly, decision making, more importantly, timely decision making. Not using research as a tool to procrastinate, but rather researching and making decisions from that research. Kind of lastly, I want to, what has surprised me the most during my projects and design experience? What surprised me the most was how much there is to learn and how much I did not know that I did not know. And the challenges of applying concepts that I've learned in classes, concepts that I read in research articles or research papers, applying those to real life. It was a surprise to see the difficulty and the depth of having to do something like that. My references, and I wanted to thank Dr. Kamzoglu, Dr. Newts, Dr. Mahdi for teaching, leading, and sharing all of what they have to know. Both time, energy, and knowledge. I really wanted to thank you all for the opportunity. And I wanted to thank my classmates for the support and the fun and being able to laugh. That meant a lot. And it was really nice to work with you guys. And I wanted to open it up to any questions that people had.